In this example, we'll look at some real data that we would be given in reference to a chemical reaction and be asked to determine a limiting reactant. And so here we have the balanced equation for copper reacting with sulfur to form copper sulfide. What is the limiting reactant when 80 grams of copper react with 25 grams of sulfur? All right, so eventually, when I want to compare amounts of anything in a chemical reaction, I need to compare amounts using the ratio in the balanced equation, which I hope by now we've established that the ratio in the balanced equation is a ratio of moles, right? It's a ratio of particles. And so often in the lab, we would measure the amount of each reactant in grams. But if I want to determine the limiting reactant, it kind of means like, okay, I've got these masses of copper and sulfur, but how do they compare to the ratio in the balanced equation? Is that a 2-to-1 mole ratio? And if not, then is there one reactant that's going to run out? And the reactant that runs out then is the one that will limit the amount of product I can form. So it's really important. It's something that happens all the time in real world chemistry. We don't always have the perfect molar ratio, but we do want to then kind of look at the ratio that we do have to see how it compares to the ratio needed in the balanced equation. Well, step one is that I can't do anything if the initial amounts are measured in grams. I got to get those grams into moles. So by now we're like wizards, right? At mole calculations. Step one, take both of the initial masses, which are probably masses of each reactant, and change grams to moles. Once you have moles, now we can compare them using the ratio in the balanced equation. So I'm looking at this 2-to-1 mole ratio. 2 moles of copper for every 1 mole of sulfur. Now sometimes you can figure out limiting and excess just by inspection. Sometimes it's not as obvious. And so step 2 is to do this. Pick moles of one of the reactants, either one, it doesn't matter. So here they picked the copper. They picked the 1.26 moles of copper. Then you're going to use the mole ratio from the balanced equation and just do a quick little mole-mole stoichiometry. We're going to convert moles of the reactant that you picked to moles of the other reactant. We're trying to find the limiting reagent, which is the same as a reactant. And so we're just converting between moles of one reactant and moles of another. And what you calculate then is the amount of the other reactant that you need. So it's like saying, if I were to react 1.26 moles of copper, I would need 0.63 moles of sulfur. Well, then you compare that to what you have. These amounts right here, these are the amounts that I have. I mean, I was given 80 grams and 25 grams, and I just switched them into moles. That's what I have. What you calculate is what you need. Now you just do a comparison. I need 0.63 moles of sulfur, but I have 0.779. I have more than what I need. So we found the excess reactant. We'd say sulfur is in excess. We have extra sulfur, which then by process of elimination, the other reactant must be your limiting. Copper must be the limiting reactant. Now you could do this in either direction. When you get to step 2, you pick moles of either reactant. It doesn't matter which you start with. For example, let's say I would have picked the 0.779 moles of sulfur. Let's say I picked the sulfur. And I said, all right, we're going to do a little mole-mole switch. We cancel moles of what we have. and we switch it to moles of what we want, which is just the other reactant. Then I plug in the ratio from the balanced equation as 2 to 1. So when I plug this in my calculator, 0.779 times 2, I get 1.558 moles of copper. And now what's important is that this calculated amount, that's the amount of copper needed. And then you just do a little comparison. All right, so I'm gonna need about 1.558 moles of copper to completely react with 0.779 moles of sulfur. So then I just take that back to what I have. And now I find, I don't have that. I don't have enough copper to react all of that sulfur. In other words, I'm going to run out of copper. After I use up 1.26, the reaction is done. And so if you need more than what you have, you have found the limiting reactant, the LR. So then by process of elimination, when we only have 2 reactants, one of them is limiting and the other would be in excess, which would then be the sulfur. So it really doesn't matter if you start with moles of copper or moles of sulfur. In either one, you take the ratio from the balance equation to convert between the reactant that you picked and the other one. What you calculate then is what you need. And we compare that to the amount that we have. If we need less than what we have, well then, yeah, I've got more sulfur, that's in excess. If I need more than what I have, then that one's gonna run out. That's the limiting reactant. Yikes! So it's like the math behind this is really simple. It's converting grams to moles and using the ratio from the balanced equation. But the concept is really sophisticated, right? It's about using ratios to compare what I have versus what I need. And so here's a really simple example using the combustion of ethene. They give me the balanced equation and they give me moles. If 2.7 moles of the C2H4 react with 6.3 moles of oxygen, identify the limiting reactant. And let's prove that it doesn't matter which reactant you pick to start with. And so, I don't know, let's say I pick the 2.70 moles of C2H4 because it comes first. All right, so we're going to set up a little mole switch. We're going to cancel moles of the one that I picked, C2H4, and switch it to the other reactant. I'm just comparing reactants or reagents. All right, so when I compare these guys, it is a ratio of 3 oxygen to 1 ethene. All right, so we're going to plug it in, which it's going to be close, right? I have 6.3 moles of oxygen. 2.7 times 3, is about 8.1 moles of oxygen. And for as many of these as I've solved in my lifetime, I always still write it in to remind myself that what I calculate here, that's what I need. If I want to react 2.7 moles of the ethene, I need 3 times as much oxygen. I need 8.1 moles of oxygen. Well, then I go back up to what I have. These amounts are what I have. And so I say, all right, I need 8.1 moles, but I only have 6.3. I don't have enough oxygen. So if you don't have enough oxygen to completely react the C2H4, you just found the limiting reactant. So we'd say then that our oxygen is the limiting reactant. It's going to run out. I only have 6.3 moles, so once that's used up, the reaction will stop. I don't have 8 moles of oxygen. And if I run out of oxygen, if you run out of a reactant, you can't make any more like CO2 and H2O if you don't have oxygen. So the reaction will stop. Now let's say we picked the other reactant. Let's say I started with the 6.30 moles of oxygen, just to prove that it doesn't matter which one you start with. All right, so I set up a conversion between moles of oxygen. I'm going to cancel that and switch it to moles of the other reactant. Plug in the ratio, 1 to 3. 6.3 divided by 3 is a big fat 2.1 moles of C2H4, and I say that is what I need. So if I want to react 6.3 moles of oxygen, I need 2.1 moles of the C2H4. So then I just look back up at the equation or the initial data given. I have 2.7 moles. So if I have more than what I need, I have extra, then I just found the excess reactant. And we'll stick to reactions that only have 2 reactants. So if you would have just done the blue work and you found oxygen to be limiting, then by process of elimination, the C2H4 ethene, that would have been an excess. Or if you would have done the work in black and you found the excess reactant, then by process of elimination, the oxygen is limiting. So you don't have to do both. We'll stick to reactions that really do only have 2 reactants. One runs out, then the reaction stops, and the other reactant, if it's not present in the perfect molar ratio, would just be left over unreacted.